got nothing to do with the lecture, but for some reason I get asked a couple of times, so I'll do a little detour for Celso. There is no negative thing, for whatever reason, if you fear it, of doing a PhD in Brazil, in South America, whatever you want to do. As long as you're motivated, you like your field, and whatever you learned, you are able to communicate that, there's a really good chance to get a PhD anywhere. It's not that I want to take away PhD students from Raffi and Celso and others, but we've had students from Argentina, like I've been working with a PhD student from Argentina, I've been working with a PhD student from Brazil, Helena Barros, on the cavity experiment, which is now used for the networking and so on. So it's like, there should be no fear, as far as I can tell you, from thinking that you don't have a chance of saying, I really, really like NV, and can I go and join a group working on NV, I don't know, somewhere in Germany. It's like, you can do it. It's like, if you are enthusiastic about the field, reach out to the professors, maybe check how to do that properly. But if you do that, I don't think that you won't be, let's say, left out in the open. That's all I can say, because, yeah, at least from our side, we do have from time to time PhD students from South America. And so far, Esteban, for instance, was one of the best PhD students we probably ever had. And there's another thing to it. You could say, well, but maybe we're a little bit weak on the hardware side. Esteban was trained theorist, and he joined us on the quantum computing experiment, and it was highly valuable and interesting for us, because we were like confident on how to fix a laser and how to tune whatever parameters, but you also need the persons who are willing to sit there and read the theory papers and be willing to transfer these concepts from theory to experiment. And so let's say more theory inclined person actually can be a very, very valuable asset in the lab. So for us, I would say the best theorists to work with tend to be the ones that are willing to sit with us and suffer with us in the lab. And so if you say you're more on the theory side, but you're willing to go to the lab, it actually makes you stronger, it makes your profile stronger. If after the PhD you can say I did a master in theory and a PhD in experimentalist, to then go on out into the world. That's the only thing I can say, but I'm also convinced that your professors, but also others in the room are more than willing to help you. So as you might have noticed, if you ask who does photons where, who does NV where are good groups, how does that work with the hiring? I can only tell you from our Innsbruck side. Just let us know, and Celso and Raphael. I mean, Raphael was also all over the place. It's at least that, as you might not believe it, but the professors are not all evil. So not all. And so usually we try to help, and if you have questions, we are there. Good. That was the first part. Second part, I brought some ion traps along, some of the newer models. You can just, there's nothing you can break, but Rafi, you don't get one. But you see some of the surface traps, how we can use them now with gold, on silicon gold, on semiconductor. We nowadays get full wafers of traps to the point where, in principle, yeah, we can just carry them around even if one breaks, so what? Because they can't produce a single trap anyway, they usually fill up a wafer with 100 traps, and so it's also nicer and easier for us to show them around. So just let them go around, and ideally they would end up here at some point again. Final part, final lecture. So now we have a little bit of time. I told you we have learned about initialization and cooling. We've learned about measurement, and we've learned a little bit about manipulation. We're going to combine all of that now for an experiment that we did 7 years ago, where we implemented Shor's algorithm. And you will see now why all these nasty bits and pieces are important, because you will learn that we have to do a measurement in the sequence, because during the measurement you heat up the register, you have to recool. That's why you need to know about measurements, you need about cooling. You will need to know the stuff that you learned from Eduardo on Fourier transform, on order finding, to combine that for Shor, and what we did at the end on how to, for instance, reduce the number of qubits and so on. I think it also gives you a very good perspective on why it sometimes helps a lot to do theory to then implement quantum computing more efficiently at higher fidelities in these devices. The slides are the original slides from 2017 when I gave a presentation in Maryland. And like one interesting aspect, at the end there will be some outlook slides, and I just checked several of the things that we were hoping to achieve in 2017 we have achieved now. And so it also shows you that it's like if you set realistic goals, you can also achieve them time by time. So here, now, Shaw's algorithm. Yeah, so that's just, maybe it doesn't like me. Short reminder, that's the ion trap. It can be in these 4 plates. We store them in a linear chain. We look at it from the camera from the side, and we use various laser beams that either illuminate the entire string or individual ions to do cooling, to do readout, and to do both collective as well as individual manipulation of the quantum register. Yeah. Okay, so we'll make it work. There is some old slides that are, it's not my niece, she sometimes looks a little bit like that, but it's just a different picture on how you can see that how ions are stored. You just use the Coulomb repulsion of the ions. Usually they would repel each other in all directions. Yeah, and what we do here is you use a quadrupole field along those axes to confine the ions. The problem is you would say, I get a saddle potential, so how could the saddle potential ever load ions? And the neat thing is you can like easily understand it from a classical point of view. It's like my 4 rods are just my saddle, my ion is a ball, it will always roll down. But then coming back to physics and classical pictures we are used to with the harmonic oscillator, we can also trap ions classically. Whatever the Paul trap is doing is the same thing there. So if it's rotating, and if it's rotating fast enough, you get an essentially confining potential. The trick part there is the rotation has to be fast enough. So it has to be notably faster than the dynamics, and that's why our trap drive usually is on the order of 30 to 50 megahertz, because then you can be sure that you have a repelling force before the ion is gone. But that's more or less, yeah? Yeah? Also. Yeah, but that's exactly when we talk about the micromotion. Don't you remember?
Around their own axis.
Yeah, okay. Yeah. No, but if you think about the micromotion, you have like the harmonic, the effective potential. This is the macromotion. But we also said that from the Mathieu equations, you get the micromotion, which is exactly with the speed, with the same frequency as the drive. And it's a little bit what you can see there, because if it's not really perfectly at the center, if you're a little bit outside, it starts to wiggle around a little bit with the trap drive. And that's more or less the same concept as the micromotion with ions. So in that system, I'll just do that a little quicker now. We have a 3-level system. We have our qubit. That's what we have, the metastable excited state. We can detect bright and dark. We can do that really efficiently. And so you can see pictures here, for instance, from 8 qubits that we've been working on. And yeah, it's just a little bit different resolution. Nice question there. First one, again, for the electronics inclined. This was an old camera. It gives you a really, really nice picture. Why do you think we would prefer such one? Why is this picture better under quotation marks? Nah. Essentially, you see that the pixels are larger. If the pixels are larger, we need to read out less pixels to get the information out, which means the readout can be faster. It's like,
what did the red pixels meant in the previous?
So that was just some color coding for brightness. In principle, it's all just counts on a CCD. It's just different way. In principle, it's also they are not blue. I mean, okay, calcium is actually it is blue, but it's just a color coding to indicate how many counts there are per pixel. Yeah, We mentioned that. We talked about the initialization, the detection time, and the operations. It's on the order of 10 to 15 milliseconds. We repeat that each and every time. Yeah, and you can make them blink. The blinking is the 0 and 1s. That's, for instance, how you would interpret it as a string with like spin if you want to think about simulations. Or, yeah?
So if you come back to the first picture which the camera shot, the one that one.
Yeah?
So they're brighter in the middle, just because there's an artifact of the lens, right?
Yeah.
It's just because it's focalized on.
Well, it's also a question of quality of the lens, question of quality of the window. It's like the more all of them are nice and round, the better your optics is. There you can already see that was the old vacuum chamber. That's the one where we don't know the quality of the viewport because it's so old. And the lens was initially, the old lens was just the second-hand microscope lens that we glued to a copper tube and we just put it in to make sure it works. And only about 7-8 years we replaced it with a better lens. But this picture is really just the very first lens that we used around 2003 or something like that. And the other ones are just then slowly getting better afterwards. There was also one trick which is easy to forget. Usually you think about the lens, I just need to put it in the center and that's it. And so if you think about alignment, you just have left, right, top, bottom, back, forth. But actually, if you have a tilt, if your lens is slightly tilted with respect to the window, to the glass window, then you can also get halo sensor on. So when we replace the lens, we noticed that this is amazingly tricky to do that properly. And so you also have to have 2 tilt axes to really make sure that the lens is nicely perpendicular to the window. Otherwise, you get undesired halos. And that's why the pictures later on went constantly better and better. If you really have essentially now 5 axes to compensate, like 3 times the position, plus the tilt, also like in terms of like left, right, as well as this direction. So the universal gate set, that's what Eduardo already introduced. So we have to have ideally single qubit gates, CNOT gates, and so on. In our case, back in those days, that was when we very early started with the Møllmer-Sørensen interaction, this XX interaction, but we could only do it globally on all ions. We didn't do the changes yet that we can do it on any subset of the ions. And now immediately was the question, wait, is that good enough? Can you, when you always have XX interaction between all ions, can you still turn it into a universal gate set? And yes, you can. But what we had to do now is to figure out if we have these interactions, well, how do you map them again, one thing to another? How do you turn a CNOT gate into a global MS gate with local operations? And so Volkmar Nebendahl and others were working on a compiler to really make sure that you can turn these typical circuits into these operations. So that was our gate set back then. So it's just collective XX interaction. We had collective beams here and at-rest phase shifts. It's just a different gate set, but it's still universal. Because think about it that way, with X and Z, I can get X, Z, and Y. And if I have it local plus collective, I can play any kind of games with spin echoes, that I can do any local operation. And together with an entangling gate, I still have the universal gate set. Something we didn't manage to do in the lecture, which would be a lecture again on its own, was characterizing how good are those gates. So far, we actually never really talked about how good those gates are. And there is one thing which is called randomized benchmarking. What you do is you take your Hadamard gate, and you apply one Hadamard gate and another gate and the pi pulse and so on. All of them need to be in a Clifford group. And because now comes the thing where you actually learn why group theory is interesting and important. It's like, okay, there is always in a group one inverse element. So what you can do is you just take a long row of random Clifford gates, and at the end you know that with a single additional gate I can always bring it to the identity operation. So this long chain of gate operations is like just a very complex way of writing down the identity. But because it's identity, you know, in a perfect world, this long chain should like give me the input state. If I start with 0, I should get 0 out. If I start with 1, I should get 1 out. Yeah, but the world is not perfect, so what you do is you should expect there is some decay in fidelity versus the number of Clifford gates that you apply. And so, yeah, okay, ideally it's an exponential decay, and from this exponential decay you can directly infer what is the fidelity per gate operation. There are a couple of small details, but you can see here, back in those days, we managed to get error rates again already there on the order of less than 1%. So the fidelities for the single qubit gate operations were already good and promising. And you can look at the details. We did also some gate set tomography, which is a more complex way of doing all the measurements. But again, you can see all the error rates were below 1% for both the identity operation, the X and the Y. And you could wonder, why do you even try to do the identity operation? Because, well, identity operation can be waiting time. Waiting time means there can be spontaneous decay, there can be dephasing, and so on. So, and even identity can have, let's say, finite fidelity. And depending on your system with superconducting, which are actually heavily dominated by environmental noise, the X and the Y gates can be really good, but the idling gate, in some sense, is actually some of the worst performing gates in these systems. You can play the same game with MS gates, or with entangling gate operations. You apply it again and again. And one way to think about it is, well, we had this picture of this superblock sphere. So if I apply it once, I get the superposition. If I apply it twice, then I'm in the excited state, all of them. And so the simple version is like you always do it twice. And then you know it should be either completely in the ground state or completely in the excited state. And then if you do it that way, again, you see we have error rates for, in that case, 2 qubits, for instance, of less than 2%, or less than 1%. And yeah, that's HO data. That's why it's at preliminary. There are different ways of how to benchmark it. Again, we don't have the time to go through those details, but no matter how you check it, the fidelities were really, really high. All of them below 1%. The coherence time in those days was worse. It's not like nowadays where we can have close to a second coherence time. So here we see we have a coherence time of 100 milliseconds, which is not that bad. I mean, it's still 3 orders of magnitude compared from a single qubit gate, which is 10 microseconds, to a 2 qubit gate, which is 100 microseconds to 100 milliseconds. So 3 orders of magnitude is more than good enough. And just for you, for AMO physics, yeah, the coupling to magnetic field can be different depending on the transitions. And so you can see here, for instance, the insensitive transition gives you 100 milliseconds. The sensitive one gives you about 20 milliseconds. And so that's how your choice of transitions also plays a role. One thing we didn't have any time to talk about, but you should know it, it's like there are a couple of extra tools which we can do in trapped ions, which really make it strong for certain applications, and in particular for sure, is we can hide ions. So if you think about it, so far we learned the qubit is either in the ground state or in the excited state, and when you measure the ions, well, there is one beam hitting all the ions, so it principally projects all ions. But sometimes Celso might say, I only want to measure the first qubit and not the rest. How would you do that? And so what we can do is we can just take a different transition, as I mentioned before. So when you, this thing, for whatever reason. So we have 2 transitions. We can go, for instance, to the -5 half state. So what we can play now is we can say, okay, let's move the electron to another state. If I switch on the light now, my new qubit, in some sense, is encoded in the D state manifold. If I switch on laser light on this transition that I usually use for scattering ions, no matter whether I'm in this state or in this state, it will never ever scatter photons. I don't extract any information. So now this ion, in some sense, is blind. What we hide it from the scattering light. Yeah?
Laser on all
on all ions, yeah?
So there
there is no way to fox only.
Well, you can, so on paper you can, but now if you think about it, it's like the scattering laser to do it just on one ion at a time. The problem is, well, you scatter 20 million photons per second. And if you have one ion here and the other ion there, one of the problems is, well, how likely is it with like the beam waste and everything that a little bit of light is on the neighboring side? And so the coupling is way too high. You can't focus down the beam good enough to really say, I just send it on one ion and not on the neighbor. It's better to do it that way because now we made the separation in frequency space and not in spatial space. And so this is one method that really helps us to measure individual ions. And then we have a couple of other tools. We can dephase the qubit. We won't need it here. But the other thing which comes in now, we can reinitialize the qubit during the sequence. It's like, you think about it, you learned about that during the second lecture when we talked about how to initialize the system. We said, okay, all I have to do is send in a little bit of sigma light. I pump everything from the +1/2 to the -1/2. So if I have a qubit, I'm starting in 0 and 1. I made a projection. How do I reset the qubit? Well, the simplest one is you take this qubit, you pump it to the +1/2 state, you switch on your sigma light, and regardless of what you did, regardless of where you started, this state, when you make these pulse, doesn't react. If you switch in the sigma beam, nothing happens. So the one state always stays a one state, and this state gets transferred down, does the detour with the sigma light, you also end up with the first in states, in the S state, or in this case, the one state. This works really, really fast and simple, and this is something which we use, which we learned before in terms of resetting the qubit, initializing the qubit, but this can be done during a sequence. So why do we need that? Together with a couple of gate operations. So here you see it's that's the Melmer-Sørensen gate. This would be collective operations. This would be localized Sharp shifts. We wrote then together with Esteban. So that's the Argentinian guy. That's Esteban Martinez. He's now with Microsoft. Together with him, when he joined our group, one of the first tasks to work on a compiler where you could take this gate set and really map from the circuit model onto the system that we have in the lab. And yes, that was something where all the experimentalists were happily taking one step back. And Esteban was like, oh, cool, now I can map the experimental part with the math knowledge that I have. And so they've written a paper then on this, on the compiler, and we used it, which we then, one of the, let's say, largest problems we were working on was really Shor's algorithm. So in some sense, now I'm repeating what Eduardo was telling you, how to factor numbers, but let's say with, from an experimentalist's point of view. So Shor, without like too much details, pick any A. You want to factor the number n. So what you do is calculate a to the x modulo n. You can do that classically. Figure out the order that happens. You calculate this a to the power of r over 2 plus minus 1, and you calculate the greatest common divisor. And then you immediately get the factors out. The recipe on paper works. Classically, it works. The problem is that finding this order classically is like not efficient. That's exactly what Eduardo was teaching you. And here is an example now from my side how you would do it. Pick, for instance, 7, and then 7 to the power of 0 to power 1, 2, 3. You get the numbers, and here you see clack, 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 and then it comes. So I immediately have order 4. You calculate 7 to the power of 4 over 2 plus minus 1, and then you get your factors out. Now it suddenly works. Yeah?
So, basic question, could that slide again? You are speaking about Shor's algorithm.
Yeah?
Let me try to understand where is the factorization.
The factorization
Yes.
happens, so like you get the factors out. It's more like a recipe where at the end you automatically get the factors of your number. So you want to know the factors of n. And so what you do is you pick any A, 7, 3, 5, whatever you want, you calculate this long string of numbers, a to the x modular n, so that's what we do here. You see 7 to the power of 0, 7 to the power of 1, 7 to the power of 2. You calculate that modular 15, you get one list of numbers. And then you would have to say, what's the order, what's the periodicity of this string of numbers? What you see is I start here, I have to do 1, 2, 3, 4 steps from 1 to end up in 1 again. And now, this greatest common divider, you just take your number 7 to the power of the periodicity over 2. Periodicity was 4. 4 divided by 2 is 2. Plus minus 1, and then you get your factors out. And the recipe, let's say, put it that way, it's classically known that it works, but it's inefficient classically. It was Peter Shaw who then noticed this combination of this modular exponentiation in combination with the Fourier transform, that's suddenly classically efficient. Quantum mechanically efficient. And the trick, I think the trick is well, maybe, but one way to look at it, here classically we had to do step by step by step. Quantum mechanically, I can replace these x here with a superposition. Because classically, I have to say, what's my x? My x is 0, 1, 2, 3, 4, 5. Quantum mechanically, I can say there is a variable. It can be in a superposition, so I just put in 0, plus 1, plus 2, plus 3, plus 4 in a superposition at once. Then my quantum computer does this entire computation of this modular exponentiation also at once. And then the trick part is like, how do I still get the information out? Because it's a superposition. If I would just do a measurement, I would only ever get a combination of the result here and the x at the top. But if you combine it with the Fourier transform, suddenly it doesn't matter. Suddenly you always get the order out.
And one additional question, basic.
Yeah?
As all my questions, you have these qubits, they are entangled.
Yeah?
Yeah. You have these qubits that are entangled. When you prepare them in a definite state, so in order to prepare the second qubit, you have to take care of the first one, if they are entangled or not.
Yeah, usually yes. But that's the circuits, like the entire way we program a computer takes exactly that into account. It's an advantage that it's entangled. It's actually, that's the way the computer is meant to work.
Okay, so that's not a problem, I mean.
No. It's actually the magic that makes the entire quantum computer work.
Okay.
So here, now we make this entire circuit again, but now we write it down as a quantum circuit. So here you see this modular exponentiation. At the top, we just call that x. We start with the input state 0, and we apply a Hadamard, like a Hadamard on all of them, which means you now get 0 plus 1 plus 2 plus 3 plus 4 and so on. At the bottom, we start with the state 1 because that's what we wanted to have. And here you now get the same thing. A to the 1 modular n, a to the 2 modular n, and so on. At the bottom here, you can make a measurement or not. You do a Fourier transform, and the Fourier transform gives you directly the correct order. That's what Eduardo did. The first time I thought, that's not intuitive at all. It's like, okay, I can write it down, but I don't see what's really happening. So what we then felt is like Fourier transform. How do we do a Fourier transform? And so this is something that you would take from any textbook. 3-qubit Fourier transform at the top, applied on some operation. In that case, for instance, some pi in that case is meant to be a permutation operation. Can be, for instance, you make a bit flip. If you do it twice, it's identity. It can be pi over 2 piles if you do it 4 times, and so on. And we looked at it and it's like, oh, back in those days, 5 qubits, ooh, doesn't look good. Couple of awkward controlled unitaries where we didn't know how to do them. Here some controlled phase shifts with small angles. That looked all a little bit awkward. But we were at the MIT. At that time, we were working with Ike Chuang. So you probably all know, like those looking into quantum computing, the book from Mike and Ike, the Nielsen and Chuang. So this Chuang is the Chuang from the MIT. And we looked at it. And I remember, I think we've been 2 or 3 weeks at the MIT looking at the thing, trying to solve it. And the thing was, it's like, oh, I think we noticed something. Don't you see, like here is a measurement. And I don't do really anything on the first qubit anymore. I can just put this measurement here and replace this coherent phase shift with a semi-classical one. I can do a measurement here, and if it's bright, I do a phase shift. If it's not bright, I do nothing. And then we can do the same thing, and if I do it here, I can also do it here. And then I can put the measurement even, like, essentially to that corner here, and just do everything classically. I measure my qubit, and then, depending on my output, I do these feed-forward operations. And then it's like, we did the same thing here, we shifted it over as far as we could, and then we noticed, wait. It's like the very moment I measure that qubit here, I don't really need it anymore. It doesn't show up in the computation. And then it's like, okay, wait. But once I don't need it anymore, the Hadamard here shows up only later. But I can move this measurement here, and the same thing here. And then we said, like, Ike, we thought we found something great. We went back in those days to Ike Chuang. We thought it's like, look, shouldn't it be possible to replace this entire Fourier transform just with a single qubit, which we just recycle all the time? And we thought we had something really, really great, and Ike looked at us and said, yes, Kedarov solved that. So Kedarov was one of the bigger theorists for quantum info. He gave us the paper. We had to read the paper 3 times to figure out where it was hidden, and it's really just one sentence where it says, like, but you can also do it semi-classically. And it took us like a week of like, how does it work? And here you can see now where we take this entire Fourier transform and we just reshuffle it as a semi-classical approach. You start with your first qubit, you do the Hadamard, you can see it here. You apply these permutation operations 4 times, you do another Hadamard, and then you do the measurement. Done. Now, we reset that qubit and we use it here. So again, you have this one, the Hadamard, you do this conditional measurement, the other Hadamard, go on, and so on and so forth. For us, it meant rather than having to work with 5 qubits, we suddenly only had to work with 3 qubits. Made the experiment already way, way easier. One thing that we haven't thought about at all, there is a contact, like when the paper came out, he called me very nervously. He's from the German security ministry branch. And he said, you have no clue what you just did. And I was like, I wrote the paper, yeah, okay. I was like, no, you completely screwed up for the, let's say, security guys, all their timelines. Because they usually were thinking, if you want to break some kind of encryption, as you heard from Eduardo, and your question was, how many qubits do you need? If you look up Shor's algorithm, if you want to factor an n-bit number, you roughly need 3 n qubits. With this feed-forward method, we don't need 3n anymore, we need n plus 1. And then the security guy was, you do know we have like a timeline for how many qubits will be available when, and when like RSA encryption needs to become nervous and so on. You said by finding and proving that this method works, and it works with a factor of 3 less qubits, you just screwed up our entire timeline. Because it might be possible to use it way, way earlier. And I was like, yeah, okay. But we still can only barely factor 15, so I think you don't have to be nervous too much. But at least it was interesting to see how much some of this scientific knowledge and demonstration can affect other fields and considerations that we don't even have on our radar.
What's the cost of resetting?
Well, cost is obviously one thing that you notice now is how long does this measurement and reset take? Because you trade off something which in principle was working in parallel with something that now has to work serially. So it's going to be slower, but actually it also has an advantage because, again, we don't have time for that in detail, but like large quantum registers tend to dephase very quickly, whereas in that case you only need like the Fourier transform, which has the information, only has to live always for very short amounts of time. The only part where the coherence has to live longer is at the bottom, but your register is a factor of 3 smaller, so the risk of dephasing is also a little smaller. So that's what we thought of. Then we started to implement it. So yeah, that's the Fourier transform. That's how you would do it with, let's say, semi-classical fashion. What we had to do was now we had to demonstrate the single qubit readout. You have to have your 3, 4 qubits, and you read out only a single one. Then the other thing was you have to demonstrate, because when you measure the ion, well, you scatter lots of photons, and the scattering is usually done, it's like Doppler cooling. So your register at the end of the operation is hot. It's not too bad, but ideally you want to recool. And we learned sideband cooling is too slow. We had to think about other methods on how to quickly recool. That's why back in those days we started to look into polarization gradient cooling, EIT cooling, and so on. Polarization gradient was for us in those days the easiest one to implement because of access reasons. Yeah, that one works, and the qubit reset we also knew how to do. So there is some details, the spectroscopic decoupling for the measurements we did already, the cooling we also talked about. Here you can see the difference from sideband cooling versus the Raman transition. So it only takes roughly 100, 200 microseconds, which is as fast as the entangling gate operation. So we knew how to recool the system. That also works quite well. And then we started to try to do a Fourier transform. And yeah, please understand, experimentalists, it's like we don't try to do the full-blown thing right away. The first thing we did was, let's do the Fourier transform alone, naked, nothing, just the Fourier transform. And then the question is like, what would you look at? It's like, okay, Fourier transform. The first time we did is, let's take an input state of 0, 0, 0. And you're like, So who can explain why 0, 0, 0 gives you that output state? So the blue is the ideal one, red was what we saw in the experiment. Why is the Fourier transform of this state, why does it make sense that this is an excitation of all little states? Come on, Fourier transform. You had a full lecture from Eduardo on it. Now I ask you to do a Fourier transform of a state and you have no clue. Why? Why does it look that way? Do you have a... Genau. So you have an input state, just a single input state. You can think of it as like in your state space, it's a delta function. The Fourier transform of a delta function is flat. All frequencies need to be there. And if you have that in your head, now it becomes clear. If I give you here 2 states, okay, now I need to have something which is more or less periodicity 2. Now you get these 4 states. Okay, again, why suddenly, why do we see 4? Wouldn't you say, like, if the periodicity is 2, I should see 2 spikes, or should there be just a single peak at 2, or what's happening there? No. That's... Now, the tricky part there is, again, just think about the Fourier transform. What you have is 2 states. And at the bottom, I mean, this is the output state as in terms of a bit string, but what's the bottom line is meant to be is frequency. So if I have 2 states, what it means is, well, there is a DC component and some frequency. So, okay, there is always going to be a DC component because in my bit string I don't have negative numbers. So there has to be, at 0, there always has to be something. And the next thing that you can then have is, okay, now I have to have something with certain periodicity. Yeah, and when you look it up here, okay, wait, I have to, that's frequency, but I want to know order. So I need to know the inverse. So that has a length of 8. So you need to divide it. And then you want to have the, I always screw that up in English, the divider at the bottom, I think, yeah. Okay. So there would be 1/4, 1/2, 3/4. So the divider here is 4, and so on. And so you can get these states. All the fidelities are correct. There are some phase shifts and so on. But the cool thing was when we did it semi-classically, we got a fidelity out of the right state of 95%. Because we only care about the populations. 95%. We would never have thought that we could get it going, the Fourier transform, as well as the fully coherent one. Because yes, we tried to do this fully coherent one. We implemented this one just for the sake of it, to get a feeling how good can we do it. Because the theorists were always like, nah, do the real thing, I want to have it fully coherent. So we did it, and this is what we got. The process only worked with a fidelity of 70%. It's still good. Back in those days, one of the best data you could get, but there is a big difference between having a fidelity of 70% for the Fourier transform compared to 95%. And so from that point of view, we also knew, okay, both methods work, but one method works notably better than the other one. Yeah?
Just one more additional basic doubt. When you say about the fidelity of being 71%,
yeah,
is that maybe 29% of the cases you won't have your 3 qubits in those states?
No, that's the process. That's the average fidelity of getting the right output for all possible inputs. So this is a description of how well the process works across all input states. It's the average for all input states, how close is the output compared to what you want to have.
Okay, so in 29% of the cases, you may not be sure that you are reproducing the qubits that you want.
No, I know which ones, but what happens is that sometimes I get a bit flip, sometimes I get crosstalk. This is all taking, is more prominent in a fully coherent fashion than just working on a single ion and recalling it. So then the next part was, okay, show me order finding. Order finding is the little brother of Shor in some sense. So you have a periodicity operation here. You start again with the superposition. You do the Fourier transform. And the question was, if you have certain operations, well, it's like the permutation operations which map onto each other, again, that's order finding. Here you have your permutation operation to the power of R. When is it 1 again? That's more or less Shor. And you want to know this R. And so we said, okay, let's give it a try. And the simplest one we could think of is in these 2 qubit register at the bottom. Well, let's start with a C0. C0, if you apply it once, it might do a bit flip depending on the state. If you apply it twice, it's always identity. Periodicity should be 2. So you give it a try. Here is some decomposition. We did the same thing with a bit flip. Bit flip, that's the cool thing. Bit flip has always periodicity 2, but with the C0, depending on which, like if your control qubit is in 0, nothing happens. If it's in 1, it does something. So you can control the periodicity of the C0, whereas the bit flip always has a periodicity of 2. And then you can apply some other rotations which on purpose have chosen, periodicities. And when we then implemented these operations here, what you can see is again the output state, for instance, for the identity. The red one is again the ideal. The blue one is what we measured in the lab. Then Toffoli gate. Everyone knows what the Toffoli is. Toffoli is this 2-controlled NOT gate. And again, now you have choices of both controls on what the periodicity is. We tried it here, we did it with a C0. Here you see with a 0-1 control Toffoli, because the 0-1 means that the Toffoli should never ever do anything because one of the controls is in the wrong state. You can do it also with order 4 and order 3. On average, we got 80% fidelity. For us, that was interesting and good because, again, we could now do and demonstrate that we more or less can do some kind of order finding at least. But you see, we gradually increased the number of qubits. We did now the semi-classical Fourier transform just working with a single qubit. Then we wanted to do order finding. We just had to do 1 plus 2 qubits. And then, yes, you have a professor is eager to push the performance in the lab and said, now 1 plus 2 works. Now you do 1 plus 4 because the 4 qubits, that's what I need to encode Shor. Because Shor factoring 15 is a 4-bit number, so you need 1 plus 4 qubits to do it with this Kitaev version. Yeah, that's what we started. The first thing was, and I think, what was the paper, Tom Wang or something like that, from Eduardo, which you mentioned, because initially we had no clue, how do we do this modular exponentiation? How does that look on a circuit model? Well, one thing was easy, this one. Can everyone see why this is times 2? Why is multiplication with 2 just a shift? So I need a volunteer. Someone raise his or her hand. I don't bite. I think I've demonstrated by now. Okay. So I have a bit like a number, normal useful decimal system that we have. Let's say 1, 2, 3. I ask you to multiply it by 10. Yeah, but what happens is we have a decimal system. If we multiply it with the number that we have in the system, all we have to do is shift it to the left. Exactly. So if we have a bit system, and if I want to multiply it by 2, all I have to do is shift everything to the top. And these are the swap operations. So these are these conditional shift everything to the left. And because it's modular, then you get the last one down. So that was the first time, now I understand where this factor like times 2 works. Yeah, and then we had to go through some of the nasty details. Okay, then you see this is 8, and then you need some additional operations. But yeah, in this book that Eduardo mentioned, you can actually partially even look up the solutions. How to do this circuit representation of these modular exponentials. And another thing that was good for us at that point was we saw, okay, all we have to do, there are ever only 2 gates that we need. We need either a swap, so like at the top it has to be a controlled swap, or a single qubit 4-NOT gate. When you think at the top, here there's always 1 qubit which controls, the Fourier transform qubit controls this entire unitary. And when I decompose this unitary, it's like, okay, there are 3 controlled swaps, there are 3 controlled swaps, and 1 multi-control NOT. There are again 3 controlled swaps, 2 controlled swapped, and 1 C-NOT, and then 3 swaps and the multi-control. So for us in the lab, we knew, if we tune up 2 gates, we can cover all of those bases. Everything else is just changing the labels on which ion it has to act, but at least for that it was working. Yeah, we used this compiler that Esteban was working on when he came to our group. We figured out how do we do this controlled swap. Yeah, it's a long sequence. It's 18 gate operations back in those days that we had to do this one controlled swap. We implemented that. There is also a way of how do we do this controlled 4 times NOT. There's another 9 gate operations. Again, that's what it looks like in some representation. And then we started to combine everything. And what you can see here is, let's say, the truth table of such a multiplier. You see the input state versus the output state, and then when we looked at it, the first thing that came to our mind is like, oh, no one can read that. I mean, mathematically correct, but not intuitive at all. And we looked at the numbers, 46%, yeah, not too bad, could be better. But we looked also in terms of what would we expect. We had 10 MS gates, we had 29 local operations, all more than reasonable good for those days. So the fidelities made sense. There was no way for us to have the professor breathe down your neck and say it has to be better. It's like it can't really be better. It's like at the edge of what the experiment can do. But at least let's figure out a way of presenting the data nicer. And so what we see is like, okay, let's reshuffle everything because it's a modular, controlled exponentiation. Let's try to split it up into when is my control 0, when is my control 1. The control is 0. Ideally, it should be identity operation. So if my input state is 0, I should get the 0 out. If it's 1, I should get the 1 out, and so on. So that should be a diagonal. That's what we got. That looked good. The other one was now, okay, if I do it times 2, so like, okay, 0 maps onto 0, my 1 state should go to a 2. My 2 state should go to a 4. Now I can start to read these matrices, and you can also nicely see that it essentially really the right states start to pop up. There are a couple of undesired states on the side, but this multiplication is really doing what it should do. Yeah, so that was times 2. We did the same thing with 7. Okay, again, here you start with 7, you get 14. It is like 2, then you go there, blah, 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 blah. All the desired states show up. Fidelities, again, they are what they are. You can do the same thing with 8. You can do the same thing with 11. And you can do the same thing with 13. So the multipliers were not outstandingly good. It's not this 100%, but at least the behavior was there. And because the behavior was there, we were kind of, okay, the Fourier transform should ideally give you reasonable numbers. So we knew the semi-classical Fourier transform would work, and we saw that all the individual multipliers do work. And then you only, that's the worst word you can ever use in the lab, you only have to combine it. So you then spend another month on only combining everything that you've done, and this is what you get. So you see 4 base of 2, you get these populations out. And now something cool happens, because the multipliers were bad. The multipliers only worked with about 50%. Yeah, but the noise actually only gives you a very small contribution at the bottom. It's like the big parts still are the right ones. And so you can really nicely determine the desired periodicity from that signal. So this SSO, that's called squared statistical overlap, that's something similar to the fidelity, but only if you have the populations. In some sense, it's a little bit along the lines of the distinguishability of getting the right output state. And so the squared statistical overlap is actually outstandingly good, because all the phases and so on, what the gate might be slightly wrong, you don't care about in that case. And I think the other more important question that came up with Eduardo, it was like, how many measurements do you actually have to do to figure out the period? And like here, when you look at that case, all you need to know is this period or this period. These ones tell you immediately what the periodicity of the system are. And you can do that shot by shot. You can do one measurement, you get a suggestion for your period because you can directly extract it for the bit string. And if you say, looks wrong, okay, take another data point. Because it could be that you end up with the DC component of your Fourier transform. Okay, then you have to redo it and redo it and redo it. But the cool thing is, only about half of the populations are wrong. Which means you have a probability of 50% with the first shot of not getting it. If you do another shot, it's like now you have a probability of 25% of not getting it. Now you do a third shot, now you're already at 10% of not getting it, and so on and so forth. And so you can see if we do 8 shots, which, just a reminder, we said before we do 100 experiments in about 2 seconds. It's like if you do 8 shots, you already can be sure that you've found the factors, even if there is noise. And if you think about it, the multipliers were wrong with a probability of 50%. And nevertheless, at the end, with just 8 shots, we can be really, really sure we factored the numbers. So the sequence, the implementation, and everything also demonstrated that this approach is actually highly resistant to many kinds of noise. Yeah, and that's why we managed to then publish it. So that was a picture of the experiment back in the old days. So this one, again, maybe for the photon people, that's where we were hiding our photomultiplier. inside the metal box so that the stray light wouldn't hit it. If we had to align something, there was this wonderful old dirty piece of cloth which was held together by a piece of wire so that you could like go through that piece of cloth and align something. That's the vacuum chamber here. For the question before about the viewports, that's what we call a viewport or a window. It's really this metal ring which is just bolted onto the vacuum chamber. The camera, the beam alignment was all over here, and there's plenty of electronics which is covered at the bottom. And if we now would think back about one of the first slides, this entire experiment here with a couple of lasers, which are, for instance, also seen over there, this entire experiment is now in one 19-inch rack. And there's nothing you have to touch anymore, because for instance, Christina, she's now operating the experiment, I think, for 3 weeks without even opening the cupboard, because it's in a cellar and she just does everything remotely. Yeah, and there you see future goals. Could we have 3D traps with some small little packaging? These traps exist. You have seen them in the presentation yesterday. The traps which are floating around are just surface traps, but yes, we can do 3D traps. You have seen that we have now the lasers inside the rack. This is something we asked for in 2017. Today we have it. We wanted to have something like beam multiplexing. The only way we could do it in 2017 was thinking about, can we have little fibers with fiber-based acousto-optic modulators to switch them on and off? Nowadays, you just have one big crystal and you have all the transducers on each of the crystals, which is just very easy to do. And the other thing is what we are preparing on is like to map from optical qubits to Raman, and that's what you saw also in the presentation this morning, that for instance, Mainz and Maryland and many others are now using the ground state qubit to improve the performance. What we were hoping for, which was one of our wishes, like can we automate the system with 20 ions? Yeah, I think we have managed to convince you that we can work conveniently with 20 ions. We demonstrated entanglement of even 24, and we do everything remotely now. It would have been good back in those days to have faster detection. That was limited with the lenses. We replaced this old lens with an O.2 lens with a lens now that can do it with an O.6. And I gave you the example from ETH, where they were showing that they can do the detection and the camera and the feed forward, all of that in about 200 microseconds. And so that's kind of almost there. They can make it faster. The branching, we were hoping to do it in 2 microseconds. We can do it now in, I think, 200 nanoseconds. So the electronics also got notably better. And then we were desperately asking, with this collaboration with theorists, can we have a unified language to control the system? Because we were always sitting there and trying to explain to a theorist, when I write XX, what does that mean? Is that like, think about your rotation angles, you always write down e to the I, some rotation angle and the Pauli, and it's like, oh, do we have divided by 2 or not? And is your sigma y with the minus top or bottom left? And these days we have that as well. So IBM, we have Qiskit, Google, we have Circ, we have Penny Lane, we support all of those languages. So essentially whatever piece of code you send to us, we can just directly execute it on our devices. And so I think we managed to fulfill all of those goals. Maybe that one a little bit, not so much, but I'd say if 7 out of 8 goals are fulfilled, then we are on a good track. And here you see an innocent picture from 2017. So where, oh, yeah, okay. Warte mal, Rafi, are you there? Okay, that's too old. Okay. So that was the team back then where we did these experiments. Good. Yeah?
The
Which one?
This one. I know, you mentioned that you can have 3D trapping, you can have...
These ones?
But how do you address the lasers? Because you have to cross off the...
So yeah, that's all the little bits and pieces that we usually would now... That's what I meant. Wann ist da drin? Ja. So for instance, what we can do nowadays, okay, we can have integrated waveguides directly in the trap, and then the waveguides go around the trap somewhere into different zones, and we use a grating to send the light up. And now, with that method, you don't have to have any windows anymore. You can just do everything right away from within the trap. And the cool thing is, you can switch them on and off here. That's, for instance, something like Mach-10 interferometer, where you can really switch on and off the light. You can send the light to various positions. That's something, for instance, from Dan Stick from Sandia. To give you a feeling how recent these achievements are, this is like a month old now. But yeah, that works, and they have been able to demonstrate also gate operations on the order of 99%. So it's very novel technology, but with these nice robust gates, like the Maserons interaction, they managed to achieve almost similar fidelities as we have. Done. So you can ask questions. So usually I would have also had, and I'll do it orally, we managed to show that we have these traps now at the distance. We can really make quantum network cards for our processors to the point where one system was like half a kilometer away from another system. We managed to entangle them. We were using a fiber to really know where the photons come and go, and we can do that telecom compatible. I mentioned that I think today or yesterday. There are new traps similar to the ones that are floating around now, where the production becomes cheaper, the capabilities becomes larger. And for instance, Jonathan Holm, in using a cryostat, he managed to show the most recent data a string of 100 ions, and because the cryostat makes the vacuum so good, he can see 2 collisions in an hour. So the string is really unperturbed and so on, so he can just also easily work with 100 ions, and you need not be concerned whether your crystal melts or something like that. And you have seen us on the very first day, we can make 2D arrays of ions. So we can like really nicely scale up the system. And one way for me to think about it is like, look, most of us have, sadly, let's say, work-induced glasses, but the glasses are always cylinder symmetrical, like binoculars. So we've seen the methods where we can move a beam around left and right. We can relatively easily do that with 30, 40 ions. If I can move a beam around 30 ions left and right, I can also, with the very same optics, move it up and down 30 ions. So going from 1D to 2D with very similar dimensions, with very similar optics, I can immediately jump from 30 to 1,000 ions. And then using an optical interface, as we have also already demonstrated, I can actually think about, can I stack traps on top of each other with a fiber link or something? And the Oxford people were able to show that they can have this optical link, just a factor of 10 weaker or slower than our local gate operations. And they are working, as I said, on this processor where they have 5 + 5 ions and a photonic interface, and they work on it as if it would be 10. They don't see, let's say, for the end user, there is no difference anymore. So it's a little bit like your multiprocessor, where it's just like how it distributes the workload, you don't care anymore. And then in combination with coherence times of an hour and more, optical interfaces, telecom compatibility, all of that, it's like I hope to convince you that trapped ions is a highly promising platform, no matter how much IBM and others promise you thousands of ions, because at the end, it's the level of control that counts. And you saw we have done 24-qubit entanglement. We haven't had the time. We were the first ones to show error correction. We were the first ones to do logical qubits, and we were the first ones to demonstrate a universal gate set acting on logical qubits with all the fault-tolerant properties that you want to have. And so maybe to round it up, whatever Kike called fairy tale, hopefully at the end of these 4 hours, or like 8 hours now, is that at least for trapped ions, the fault tolerance is not a fairy tale, but we have demonstrated it. And then ideally, the next time I come by, you will have your own ion traps here and someone doing some really cool physics on it. So there might be, not now, but there might be positions available for PhD students soon.
We hope so.
Yeah? Good. Now I think we can go into questions. And who has seen my traps?
Where is the trap?
Yeah? So sorry.
Once again, a basic.
Again?
Well, once again, a basic question.
Sure.
So, if you want to do some mathematical operation, you have to make a setup of your whole equipment in order just to do, for example, 2 plus 3.
So in 10 years ago, it would have been a major problem. Today, if you want to do 2 plus 3,
yes.
actually there is a Python-based quantum computer program language from Qiskit, and you can essentially program it. It's like, what's the adder function, and just do 2 plus 3. You can write this code, and all the magic in the background happens automatically, and you can just run the code on our device directly. You don't have to know about ions. You don't have to know too much about quantum. It just works right away.
Okay.
But it took, I mean, these are the old slides were from 2017. So it took like 5 years for someone to work on this language. And if I may something, like one thing, is like during that time, we've been in projects together with IBM. And no matter how much you might like or dislike some of the marketing activities that we do, but at the end, I'm very much grateful for the work that they do, because without their effort on establishing a really, really good quantum programming language, like I wouldn't have the resources to work out a good quantum computer programming language. It was so valuable and easy for us to say there is a language and we just have to write an interface towards that language, and everything else is taken care of by IBM. And that makes it easy for you, that makes it easy for me, and no one of us had to spend a single euro or real or something on it.
Thank you.
Okay, that's too far to throw. You switch it on.
Thank you, Professor. I meant to ask, because you said electronics are noisy. So while implementing a quantum algorithm, at which moment do you apply error correction?
Again?
While implementing a quantum algorithm on the quantum computer, at which moment do you apply error correction? So because the electronics are noisy.
It's like we did error correction. We did it the normal 3-qubit repetitive code. We did topological codes. We were able to show all of that. At the end, it's a question of what you want and not so much about what I can do. Because the trade-off is, for a topological qubit, one of the smallest sized systems, you need 7 physical qubits to work with to get 1 logical qubit. And if you now say, I want to run some interesting algorithm, you saw with the Fourier transform, if you want to do a smallest instance of Shor, we already needed 5 qubits. So if I want to do that with logical qubits, I need 7 times 5 plus the ancillars for the readout. So I need something like 50 qubits with very, very high fidelities. And no one has 50 qubits with high fidelities. IBM has 400, but the fidelities are not there. Otherwise, they would do error correction. And the ones that do error correction tend to focus on something closer to 20 to 30 qubits. And so I can give you either 2 really, really good qubits, but with 2 qubits it's like a little bit boring. Or I can give you 10, 15, but then you have to work with higher error rates.
Thank you.
More questions? Good?
Thanks again, Professor, for the talk. Very enlightening. Coming back to the interface between Qiskit and Penny Lane and your platform, those languages are established, but they are changing a lot because new libraries come in or new methods. So you are continuously checking on these changes? And
no. So we did support, or we do support in principle all of them, but we noticed that about 95% of the stuff that people send to us is Qiskit. And for whatever reason, because I think it's just Penny Lane which focuses more on machine learning, there are a few rare instances where people ask us to run Penny Lane code. But this is really usually more in this context of quantum machine learning. So these two are still used, and like we just didn't update the API for Circ and others, because like why should I do the work if no one wants to use it anyway? And so if 95% of the work is covered with Qiskit, we just try to stay up to date on our interface with Qiskit, and that's good enough.
Yeah, I was thinking about that because, libraries or methods for machine learning from Qiskit are relatively new, and they are appearing day per day, and so.
But the cool thing is these are higher level libraries. For us at the bottom, at the API level, it hardly doesn't affect us. Because the API only communicates sequences going back and forth. Yeah. Whether you then have some additional machine learning added on top of the raw data, it doesn't change anything for us at the bottom layer of the stack. It's like you can also run new software on your laptop. It's like as long as the APIs and everything support what you need, then you can run an old Word and a new Word on your laptop. And so that's the same for us. As long as the API can do whatever the newest version can do, then there can be 100 new libraries on top. Doesn't really matter for us at all.
Okay. And one final question. Are there any available positions on your how do we apply or something like that?
What's my answer now, sir? So, bottom line is, if you want to apply, just do it. But be aware, the way we currently run our group historically has grown out of Rainer Blatt, which is now more or less split up into 4 different subgroups now that Rainer Blatt is emeritus. Usually on purpose, we understand that if you're not local or have been local, to understand how the experiments are sometimes connected and so on. So if you apply, we usually make sure that the person who applies gives a presentation, and gives a presentation essentially for all the ion trap groups. And then when you visit, because we want to make sure that you get the feeling for the group and the group gets a feeling for you, whether you fit in with like team chemistry, you spend like at least 3-4 days in Innsbruck. You go through all the different experiments and groups, and it might be that you visit and say, I really want to do quantum computing. But when you are there, then you might get, for instance, into a group from Tracy Northup about the networking. And then you say, but yeah, okay, Dom is not too bad, but actually working with Maria on the cavity experiment would be way cooler. And so that's why, let's say, it should be at the end, our goal is to make you happy, because if you are happy on what you do, the research that you do, then you will be there in the evening, you will be there and push forward even if it doesn't work too smoothly, because that's the problem we sometimes have in the lab. But if you like the topic, it's way better that you like the topic and you have a really a PhD that you like, rather than me forcing you into a particular direction to say you are either doing computing or nothing else. Because then how would you stay motivated for more than 4 years that we usually have a PhD in Innsbruck? And so, yeah, you would work, for instance, see the labs from Christian Roos on quantum simulation. You would talk with the experiments from Philipp Schindler on charged molecules and whether you can do spectroscopy on charged molecules. Martin Ringbauer is now working more on qubits, because the idea is, imagine you saw the lever scheme, there are way more levers than just 2. And so his suggestion was, if I take not 2 but 6, 7, 8 levers, wait, if I take 6 levers, that's like 3 qubits. If I have 20 qubits and I can control 20 qubits really, really well, 20 ions, that's the equivalent as controlling 60 qubits very well. And then suddenly you would be exactly in this regime of quantum advantage. But you only need to control 20 ions, but you control the Hilbert space of 60 qubits. And so it could be that you come here, but then you say, but the idea for Martin looks promising. I'd rather want to do my PhD with Martin, and I won't hold you back, because it's more valuable that you are where you are and you don't get pressured into a direction which might help short term for a year, but then maybe after a year or 1.5 years, it's just like, it turns into 9 to 5, because we don't have time for 9 to 5 work. But that's a general recommendation. If you think about joining a group, don't go there for an afternoon, but go there for 2-3 days, get the feeling for the group, talk with the students besides the professor and say, is he cracking the whip? Is he someone I can talk with when there is a problem? Is he available, or is he gone the entire time? This is something you can get from the other fellow students. Get a feeling for the students, how the group is run, how many meetings are there with the professor? Is it once a month? Or is there micromanagement that he's there every second day? Yeah, it's more questions? So, yeah. Done.
Hello. Okay. I think it might be a little bit off subject, but I would like to continue what he was talking.
Yeah.
Because you advise us to go spend 2 days in the lab, but well,
not in the lab, 2-3 days in the group.
Oh.
Whether it's a theory group or not, or experimental, you just work with the group, get a feeling for how the group is run.
Okay, so also like remotely and...
Well, remote. I'm not a big fan of remote.
Okay. It's because we usually can't just go to the groups, because most of the groups are really far away. So I was thinking about remotely would be the only option for most people, I think. I would like to get your advice, actually.
Is it like, okay, maybe it's different, but for us, if we say a person is valuable and we want to have him in a team, I mean, yes, we fly him in. Even like the full, let's say, interview is flying the person in, and he or she stays 3-4 days in Innsbruck. I mean, how would you get the proper feeling for, like, really, it's like you come into the group, and you do it similar in Stockholm. It's like most of the people use these methods. You fly them in, you give a presentation of what you did. If you give a presentation of what you did, we get a feeling like, how much do you know about the details? Can you present it? Because if you understand it well, you can explain it. If you explain it in 2-3 different methods, you have really thoroughly understood it. Did you like it? Maybe explain, and that's not a problem, but like say, maybe you did something theory, now you want to do experiment. Or maybe you want to go from, I did quantum info, now I want to do cold atom physics. Just be able to explain why you changed direction. Maybe you said like, I did it for a year, I don't like it anymore, I want to change fields. It's a completely valid answer. But then after that presentation, people get a feeling from what you present, how thorough you thought about things. Maybe there's a nice typical question like, if you would start from scratch, what would you do differently? What was a waste of time? Yeah, and then get a feeling for the group. For us, it means, okay, you do lab tours, okay, for us, but you spend time with the team, but you spend some discussion time with the professor. We on purpose encourage then the visitor to like go out for dinner with the team, because later on you will very likely do the same. We take care of the costs again, just so that if there's a Gabriela, that's like, oh, come on, no, it's like she's been here 3 days, no, never once opened her mouth, just floating around like a ghost in the lab. This will be hard to say the group, it would be cool to work with her. But if Gabriela is in the lab and she says like, okay, she notices this, she has a couple of questions, she makes connections, she shows interest, then the people might say, ah, that would be someone really cool. And she brings in some photon background and we want to do, let's say, integrated waveguides. That's something we need anyway, and we currently have no one who does integrated waveguides. Wouldn't that be cool? To give you a feeling, the next postdoc we are going to get has done nothing with ions, nothing with optics at all. But for the new traps, which are somewhere here, you see we need and work more and more with semiconductor industry. So he did actually his PhD in semiconductor fabrication. And he came by, we had like almost a full week of discussions, and he's like, oh, how do you do it? Have you thought about these layers? Are there some different methods? We need, and he did fit into the DEAM chemistry. And so now a non-quantum optics person is going to be a postdoc on one of these experiments. We had theorists, and if I could, I would immediately take someone who did computer science to help us get better with automation, interfaces, and so on. And I know, for instance, maybe also interesting for your different direction, have you thought about computer science? So like I know at our university, the computer scientists would be eager to do a little bit on quantum, but typical computer scientists don't get trained on quantum. So they are very interested to say, can I find a theorist who is like more, let's say, mathematically inclined? Can I find a theorist who wants to do a PhD in computer science and quantum in my group? So it's your options compared to maybe 10 years ago are way broader now, because it's not you do theory and you keep on doing theory. You can go say, maybe I join an experimental group because they need more and more interdisciplinary knowledge. Or you say, nah, I go into computer science because that makes it easier for me to work for some of the larger companies. And I can do computer science and quantum. But I'm not an advisor. Maybe Celso or some of the local professors want to do. What else?
There.
Huh.
Hello. Hello. Thank you again for the presentation. It's a silly question. How long it takes to make the benchmark in the error by Clifford gate?
That's a cool thing. It's like you only need to scan the length. So if you want to say, I want to go, like you do 1 gate, 2 gates, 3 gates, each of them with reasonable good statistics, let's say 100 repetitions, and you do 100 steps. Yeah, okay, it's 100 steps times 2 seconds, so a full benchmark is then done in 3 minutes.
Yeah, that's really fast. And you use all the gates you have, or just the Clifford gates?
So no, that's a cool thing. Randomized benchmarking, due to the underlying theory, only works for Clifford gates.
Yeah, but you extend the theory, like you try to all the gates?
No, we did. So together with Joel Wallman and Joe Emerson, there is something which is called cycle benchmarking, where you can also benchmark non-Clifford gates, where essentially what you do is you just combine a few gates to make it look like a Clifford gate.
Yeah, and then you have identity metrics.
Yeah, well, no, you don't look at it. It's still the success probability, so still it's some kind of error amplification. But it works. But yeah, then you can go down another rabbit hole, because the question is, for instance, if you do composite gates to generate a Clifford gate, so your Clifford gate always consists of 3 gates. The randomized benchmarking only tells you the error per Clifford. Imagine now the error per Clifford is 3%. are you allowed to say, well, my Clifford gate has 3% error, does that mean each of my gates has 1% error? Because it could still be, if you're not careful, that it's actually one gate has 2% errors and the other two have 0.5% error.
So have a composition.
So you need to twirl and do that, and yeah, there are a couple of, like, if you want to, if this is something that interests you, you need to talk with Joel Wallman and Joe Emerson at IQC in Canada.
Yeah, okay. Thank you.
More questions? So if there are none, there's one final remark from my side. I talked with Umberto, and ideally there should be more, I don't know, fruits, juices. I just say organize something more, because at least lecture-wise, that's my last lecture. So I hope whatever it is that Umberto organized, that there is more outside so that we can have a better time talking and chatting and being around. Good? Done?
Thank you very much. I just would like to thank so much Thomas for these very nice talks, very nice lectures. And I hope you students have enjoyed a lot these courses this week. So Eduardo started doing basic courses about quantum computing, basic logic gates, theory, how to derive the Shor algorithms, and now we end up with the Shor algorithms implemented in the lab. So this is very nice, very cool. Thank you very much. I hope you have enjoyed this time. Tomorrow we have more.